In my opinion, NumPy is what makes Python Python. Without NumPy, Python iteration is too slow. You can't really work with loops too easily. You can't really work with big arrays too easily. With NumPy, you can do what you'd normally need a loop for super fast by using really well optimized C methods. Because NumPy is so simple, a lot of people have no idea how it works, don't even know how C works because you don't need to know those things, and therefore they miss out on how genius NumPy is. In this video, I'm gonna break down how it actually works under the hood for you so you guys can all appreciate NumPy as much as I do. So I started looking into NumPy about 3 months ago when I was in an AI class, and I realized array.t gets you the transpose, but no parentheses. So is it a function? Is it like, what is that? How does that work? How does it get a transpose? Is that a property that NumPy is always storing? I started Googling things, asking ChatGPT questions, looking at a NumPy source code, and I think I have a solid understanding of the basics of NumPy now and how it works under the hood. And honestly, it's amazing, and I think I can convince you to be as big of a fan of NumPy as I am with just 9 lines of NumPy source code. The first 2 lines we're going to be looking at are the header and footer of a struct. They're the standard struct header and footer for a Py object with just a name. There's nothing special, it just helps NumPy wrap it into Python. So now let's get into the real stuff. This line says char pointer data. C types don't change. They're explicit, they're determined at compile time, not runtime, and Python and its users don't care that much about types. So if you want Python users to like your C array package, you need a way to take a statically typed C object and let Python users not worry about different array classes for different types. There's a few ways you can do this. You can make 10 different arrays and wrap them all into one complex multiple class using the Python API, or you can be an absolute Chad and ignore types altogether. Data is not really a character. The reason the character was chosen is because it's a simple 1-byte data type. Think of this byte like a brick and our array as a brick wall. Normally, the way you navigate the wall is that your array variable counts as the address of the first character, where that character lives in memory. When you go up 1 index, you add the size of the data type of the array to that first address, and then that takes you 1 brick higher on the wall. This lets you instantly access anywhere on the array just by knowing the first value and how far ahead the other value that you want to access is. What NumPy does is it treats each brick as a building block for a single element. So if your data type is an int, that's 4 bytes, 4 characters, 4 bricks. NumPy instead takes the address you're asking for, and instead of using a char pointer, now treats it as an int pointer, getting 4 bytes instead of the 1 byte, forcing C to treat the address as that it would normally treat as a character, because remember, it was declared as a char pointer as an integer. The craziest part is this doesn't hurt performance. It's not joining things, it's just pretending that the next character is an integer and getting it the same way it would get an int. Because of this, it doesn't really matter what the NumPy user wants their data type to be anymore, as long as NumPy can kind of figure out what the data type's supposed to be when the array is created. This line is a macro for the Python API. All a macro is when code's compiled, the preprocessor basically just injects different code into here. A macro is just a stand-in for different code. In this case, this is just a pointer to a certain Python API class, but I'm using this line as an excuse to talk about macros across NumPy. If NumPy didn't use macros, they'd have one of 2 options. Either every function would need to be implemented once per data type. You want to have a certain function that copies an array, you need an int copy, a double copy, a float copy, over and over and over, and it's just too complicated. Or you would need to have every individual contributor on a massive open source project with a bunch of contributors always keeping track in their head. Okay, so at the start of this, I gotta remember I can treat this as an int, a float, a double, a bunch of things, and then telling the computer to treat this as a double in this case, this as a float in this case, and it just gets really complicated because you need to keep track of the exact number of bytes and the spacing and the loops, and it would just drive people insane. One, if you've ever had to keep track of individual bytes when you're writing code, it can drive you and it can kind of start to give you a headache. And two, you're gonna make an error that's gonna cause a security vulnerability. Maybe not one person specifically, but across all the contributors, eventually there will be a security threat left open, and someone's gonna be able to hack all the code that uses that NumPy function just because of that. What the macro does is it says, just write this and give a bit of information about the struct, and it will inject whatever type you need, whatever spacing you need for your loop, all the different things that could be problems. Don't worry about them. We're solving them. You as a contributor don't have to worry about them. As a Python user, you definitely don't have to worry about them. But even the contributors don't have to think about the data types. They can just write a function for numbers, have it work for doubles, ints, floats, whatever, and not think about it. No risk of security breaches from a contributor not being able to keep track of things in their head, and no risk of having the repository unnecessarily explode in length because contributors kept writing like really long functions over and over and over again, once per data type. So this line actually doesn't seem that crazy at first because, well, we've already explained, NumPy allows one struct to be multiple different data types. So of course it's gonna have a line that explains what the different data types are. But I just wanna show you guys how much goes into determining what a different data type for NumPy is. This line is a pointer to another struct. That struct explains in depth everything about how the bytes are arranged. Is the first byte the biggest, the start of the number is the first byte, the end of the number, what kind of data type it is, and just a bunch of information about how to read those 4 chars that make a float, 8 chars that make a double, and turn them into the float that the user wants to see. Not only that, but if you look at it, this struct's almost entirely characters. If you were making something that could be class 1, 2, or 3, or 0, 1, 2, 3, you would use an int. Be honest with me. Most of you guys would use an int. I'd use an int. That's just what you'd use. But no, characters, because it's a 1 byte, no need to take up the extra 3 bytes in memory for something this simple. Even if it's only used once per view of an array, 1 byte. And that's just beautiful, honestly. Int nd. This line is what kind of starts to give away what makes NumPy work as NumPy. We only have a single dimensional character array, and yet nd is the number of dimensions we're going to pretend that array has, letting us make it into an any dimensional array. To explain why NumPy arrays being flat is so important, let me show you what one of my arrays would have looked like before I started reversing NumPy. Basically, what I would have done is I would have started with a float pointer pointer. This gives me an array of float pointers, because remember, we can just treat an array as a pointer, so a pointer to a pointer is an array of arrays. That means I'd then have the ability to fill an array with a bunch of arrays of an inner size, put a bunch of pointers at that pointer and at the addresses after that pointer of a bunch of arrays of an inner size. Then all the inner arrays wouldn't actually be connected to each other. So if you're following what I'm saying, you'd realize I would need an extra row of the length of the number of subarrays to keep track of where each array would go. This actually kind of works if you're just working for yourself. As you can see, you can access this at this index and this index, and it works. It makes sense for making an array for yourself. But if you're making a library or trying to make an efficient array, it's not that good. Let's say instead of 2D array, you now have a 3D array. Now, instead of having one extra row, you have one extra row in the 3D array to tell you where each of the extra 2D array rows is, and then each 2D array has its own row to tell you where all the data is in the 1D arrays, and it just gets complicated. Every time you add a layer, You create another set of extra rows and multiply all the previous layer's extra rows by the number of subarrays you want in the new top layer. Another big problem you can run into is, let's say you have an array that's supposed to be your Y for a neural network's output, and that neural network only has one output node, one output neuron. So all of a sudden you need your Y array to be a two-dimensional array. So a subarray, but each subarray only has one element. If you use my float pointer pointer structure, you're gonna have double the amount of storage being taken up than if you take NumPy's much smarter, more elegant approach of a flat array that gets treated as a multi-dimensional array. The dimensions of an array is actually just its shape. One really interesting thing I've learned while researching NumPy is that they use size variables instead of int variables for sizing of an array. The problem with a regular int is that it can be negative, it's kind of a small data type. A size is generally a long and it's unsigned. That means if someone passes -1 as the size of an array, you don't accidentally allocate 9999999 because it's 2's complement, -1's just a bunch of ones, and then it's a really large positive number if it's treated as unsigned. Just treat everything as unsigned if you're making a production quality array, and that makes things way more efficient and way less prone to errors. Of course, if you're working on your own, the natural way to do things is just, oh, int size equals 4, because that's just where your mind goes. But that can create a ton of errors later on, especially if your array is going into production like NumPy in just about every industrial Python code out there. Dimensions itself is just an array to describe the size of different subarrays. So if you have 8 ints in each subarray and 4 subarrays, NumPy will understand that on the brick wall it's looking at, 4 bricks make a section, 8 sections make a subarray, and 4 subarrays make the whole array, because the shape would be 4, 8. Shape generally acts as the max loop control variable. So if you want to ignore some data, let's say you write some code and you decide there's an array with 10,000 elements, but element number 10,000, that was kind of an outlier. It's a sorted array, that's the biggest one, it's way too big, and you don't want your ML model seeing it, so you just want a NumPy array that's the first 9,999, but you still want element 10,000 in your code, because when you make the final charts and reports, you're still gonna have it. Maybe it's still in your test data or something, whatever. So what you can do is, instead of duplicating the array, you can just create a second NumPy array that's a copy of the first one, in the sense that it has all the same information about it, except its shape, the first element in its shape array, is just one less, and it'll still look at the same data on the heap. It won't allocate any more memory, but this new array is going to be the exact same thing, just without your last outlier element. Now this sounds pretty complicated, so you might be thinking, oh, I wonder what that array would look like. Like, how would you even make something like that happen? Turns out it's literally just this code. It's that simple. It's just one line to do all of that. No copying, no nothing, just altering shape a little bit. That is the beauty of NumPy. NumPy is just returning views of the same data living at the same address space. You could get 3 different array objects all saying completely different things. Maybe one's the X of your data, one's the Y of your data, but all the data is stored at the same place in memory. It's just being looked at differently, and that's all different NumPy array objects are on the same data, just different ways to look at it. You might be thinking to yourself, okay, that makes some sense, but it doesn't seem like shape alone is enough to do all of that, and you're right. You are completely right. Let's say you have a 2D array that you're going to train an ML model on. It has 10 elements in it, 10 different data points on your data set you're going to train your model on, and the first 3 are attributes, the last element's a label, and you want your last element to be on one NumPy array, your first element to be on an X NumPy array. You would just do this. That makes sense. But shape alone doesn't really explain how you'd be able to make this change. Stride is what makes this possible. Let's just say that we have a two-dimensional array to make it easier. Though by default, the last element of strides is always going to be 1. The second to last element of strides is the length of each subarray. So if we have 4 elements in a subarray on our 2D array, then strides would be 4, 1. This means you jump 4 indices across the brick wall for every first number in the brackets, and 1 for every number after that, letting you navigate the entire brick wall rather than just looking at a specific pile of bricks from my array approach, like where I say, oh, this is the first index, go to this address to find things on the first subarray. That's where the first subarray starts. All right, you get to that address, you go somewhere. In Numpy, you instead say, you go to the first address of the first subarray, jump 4 to get to the second subarray, 8 to get to the third subarray, and then you can go 1 to get through each element of that subarray. That's what strides is saying, and it allows us to flatten out a n-dimensional array into a one-dimensional array and still treat it as an n-dimensional array. Let's go back to that example trying to split a NumPy array into x and y components, the x being the first 3 attributes of each subarray, the y being the last. When you run this script, this splits out the x. It tells x, you are a two-dimensional array, nd equals 2. Your shape is 10, 3 because we have 10 samples and each has 3 attributes. Your car pointer data is the same element as the main array because that is the start of the first attribute. Because you have to ignore the last element, your stride is 4, 1, meaning each new subarray is 4 elements apart, even though your shape's only 3, so you can only look at the first 3 elements of each subarray. Your stride makes you jump 4 elements to get to the next subarray. This way, you're going to skip all the y values, and you're just going to have an x array. Let's say for this example, we want y to be a one-dimensional array. This code tells y, you are a one-dimensional array, nd equals 1. Your shape is 10 because you have 10 samples and each sample only has 1 label. Your car data is the first address on this part of the brick wall because this is the first label. You're not the first address of the original array. You are the 4th address in that array's data. Your stride is 4 because that is how far apart each subarray is, which means that's how far apart each label is, which means you need to jump 4 to get to the next label. Now let's say we change our minds. We want x to be 10 element subarrays, 3 of them, each one for a different attribute. Attribute 1, each of its 10 data points is in the first subarray. Attribute 2, each of its 10 data points is in the second subarray. So we want to transpose x. Why can we just write x equals x dot t? How does that fix our problem? Well, what that does is it calls transpose. It actually is a function. I thought it was a statically stored property. I misled you at the beginning. It's a function call. I was wrong. It's an O of 1 function though, meaning that when it's called, it has a constant time. You could have a 10,000 by 10,000, 10 million by 10 million array, if you could fit that on your random sticks, and it will only take a constant time, same amount of time as it would to transpose a 1 by 1 array. That is fast. The trick? You're not actually creating any new data. You're not changing anything. You're not doing anything complicated. You're just flipping strides. So if strides was 4-1, now it's 1-4. Your shape isn't 10-3 anymore either. It's now 3-10. You just flip those 2 arrays, and that's a transpose. Don't believe me? Let's walk through it. First, not transposed. I want to access my first element. It's just 0, 0. That's just the data address. If I take a transpose and I flip stride in shape, that's not going to affect accessing 0, 0. It's the same thing. It's just returning data, the car pointer data, the data there. That's not going to change anything when you change stride and shape. Now let's say I want to access the second element of the first array, or 0, 1. That would be at data plus 4 times 0 plus 1 times 1, or this right here. Pretty clearly the next element. Now let's say I want to do the same thing on a transpose view of the array. Access the 0, 1 element. We could all agree that it would be this brick right here. So is it actually? 1 times 4, the second element of the tuple, times the second element of strides, plus 0 times 1, the first element of the tuple, times the first element of strides. That gives us a jump of data plus 4, and we're there. This is a really cool line because it works so nicely as like a season finale for this video. It's simple enough that I wanted it before the last line, but it only makes sense if you know what a view is and how stride works. Basically, it's just a pointer to the original view that first handled the original data address. This way, when you transpose something, transpose it again, transpose it a third time, you don't end up with a long chain of different views pointing to each other. Every view points to the original array. It makes managing the memory a lot easier when you're cleaning things up, and just makes everything a lot easier for NumPy to work. So there are 4 more properties I left out of the array. From what I understand, one of them kind of manages memory access. It's a flag for like reading and writing permissions and stuff. And the rest are just Python access, like binding things that are needed. I don't fully understand these, and they're not that important in the function of the array, so I left them out. I hope you can start to respect how complicated NumPy is. What we looked at was just the start. You don't finish making NumPy when you finish implementing those 9 lines and you finish implementing the things that make those 9 lines work. That's when you can start building the linear algebra and start building the other array functions that the package has to offer. It's super in-depth, and I really don't think the Python language would be what it is if it weren't for NumPy coming in and making it so much more efficient. So thanks for watching, and if you made it this far into a video this long without stopping watching, and you're not preparing a hate comment for how much terrible my video was, then take a second and subscribe. Thanks for watching.